Throughout much of our study of chemistry, we've looked at how reactants change into products, and we've asked questions such as how much of this product will be formed, how much of A and B are necessary to make it, what is this product, is it a solid, is it a liquid, is it a gas, what kind of phase of matter will it be, is it a precipitation reaction, redox reaction, what's the stoichiometry of this reaction, and what do we have to make it, what will be left over. Well, in Chapter 14, we take a little break from those types of questions, albeit we use a number of those ideas throughout the chapter. But this chapter asks the question, how fast will this reaction take place? The area of chemistry that's concerned with how fast something changes or the rate that a reaction occurs at is called chemical kinetics. And Chapter 14 is called Chemical Kinetics, and in that we'll study reaction rates. Make sure that you have your packet in front of you that lists all the note guide and the places for you to write down the various notes, starting with section 14.1 where it says factors that affect reaction rates, as we'll be filling those in and taking some notes along with those throughout this video cast. There are 4 factors that affect the rate of a reaction. Factor number 1 is what is called the nature of the reactants. The nature of the reactant is the physical state of the reactants. Of course, if something is ground up and has lots of surface area, as in a demonstration we've done with a lycopodium powder in the past, it's going to react a lot faster than if you just take 2 blocks of something and bang it together. If something is in a liquid or a gaseous state, generally it reacts quicker because the molecules or particles are able to flow past each other and move quicker and react with one another. So the nature or this physical state of the reactants is factor number 1. Factor number 2 is the concentration. The concentration of the reactants. And concentration we generally measure in chemistry is in molarity. Molarity, remember, is equal to moles divided by liters, or if you remember the molarity triangle, molarity equals moles divided by liters, and we'll be using that molarity triangle a lot during this chapter. The concentration of the reactants, whether it be in moles per liter or in parts per million or whatever concentration it is, makes the reaction faster or slower. Thirdly, the temperature at which a reaction occurs. Usually, as you increase the temperature, molecules move faster and they react quicker, and we'll take a look mathematically how that usually is true. And lastly is the presence of a catalyst. A catalyst is a substance that speeds up a reaction without actually being used up itself. Just the simple presence of the catalyst makes the reaction go faster, and we'll take a look at how that actually happens on the molecular level. Section 14.2 in your textbook talks about reaction rate and generally focuses in on one of these factors, and the factor that it looks at most is concentration. As a matter of fact, the next 3 sections, 14.2, 14.3, and 14.4, takes a look real closely at this factor of making reactions faster. Not that we're ignoring the other 3, but we're going to focus mostly on number 2 over the course of the next 3 sections of the chapter. 14.2 talks about something called a reaction rate. The rate of reaction is also known as the speed of a reaction. And generally when we look at the speed of a reaction, we look at how the molarity changes with a unit of time. And so generally we'll measure the speed or the reaction rate in molarity per second, or molarity per minute, or molarity per year, depending on how long the reaction takes place. We look at how the concentration varies with time. It's known as its reaction rate or its reaction speed. How does increasing the partial pressures of the reactive components of a gaseous mixture affect the rate at which compounds react with one another? Well, if the components are gaseous, there's a relationship between pressure and concentration that we need to know and understand for the rest of this chapter. Remember, when you increase the concentration, when you increase the pressure of a gaseous substance, you take those molecules and you squish them closer together, and so there's more parts per unit volume. And so if you increase the pressure, technically what you are also doing is increasing the concentration of the reactants. And so pressure could be said to be directly proportional to concentration, even though pressure is the unit of, quote, concentration, unquote, for gaseous mixtures of reactions. So when we say we increase the pressure, always think, hey, we're actually just increasing the concentration. And so we could take a look at reaction rates in terms of how does the pressure change with unit time as well. And we're looking at the same thing, although most of the time we'll talk in terms of molarity as the concentration. Taking a look at these pictures now, which are on page number 577 in the 10th edition of the Brownell-May text, we can use them to help answer sample exercise 14.1, which says, from the data in the figure above, calculate the average rate at which A disappears over the time interval from 20 to 40 seconds. Here we're told that we have 1 mole of A. Here we have 0.54 moles of A after 20 seconds, and at 40 seconds we have 0.3 moles of A. And so we want to look at what's the average rate that A disappears from 20 seconds to 40 seconds. So speed or rate for us is defined as the change in the concentration divided by the change in time. Change in concentration divided by the change in time. And if we look at this, we start with we end with 0.3 moles per liter, or 0.3 molar. And we started back here at 20 seconds with 0.54 molar. That's our change from final to initial. Okay, and then our time goes from 20 seconds to 40 seconds, so 40 minus 20 seconds. Notice our units will now be molarity per second that it will be changing at. And if you notice, 0.3 minus 0.54 is going to give us a negative value. Why do you think we call it a negative value for something that's disappearing? Well, that's exactly right, because it is disappearing, and since it's going away, we say that we lose a certain number of a certain amount of molarity per second. So if you take these two numbers and do the subtraction and you divide them, you end up with negative 1.2 times 10 to the negative second, and the units are molarity per second. And one of the ways the chapter absolutely loves to write units is to write it as molarities times seconds to the negative 1, and taking a lot of these units that are below on a fraction and writing them simply with a negative exponent. Get used to that this chapter, because you use that a lot. Practice exercise 14.1. For the reaction in the figure above, calculate the average rate of appearance of B over the time interval from 0 to 40. So now we're going to look from 0 right here up to 40 seconds, and we're going to ask, what is the appearance of B? Well, if you look at the start, there isn't any B. If you look at the end, there's 0.7 moles of B, and since it's in a 1 liter container, we're going to look at the rate of appearance of B, and we can write the equation that that's going to be equal to the change in molarity divided by the change in time. And our molarity changes. The final molarity is 0.7 molar. The initial molarity is 0.0 molar. I mean, we started with none here, right? 0 moles at the beginning. And then we'll divide that by our time. And the final time is 40 seconds. And the initial time, of course, is 0. And notice now we're going to get a positive value, 0.7 divided by 40. And notice the units, once again, are molarity per second. I forgot to write the seconds in there. And 0.7 divided by 40 is 1.8 times 10 to the negative 2. And the units on that are molarity times seconds to the -1. So that's a positive value. And the reason it's a positive value because it looks at the rate of appearance of B. It's the thing that's appearing, not the thing that's disappearing. So keep your units straight. If it's or keep your sign convention straight, I should say. If it's something that's disappearing, it's going to have a negative value. If it's something that's appearing, it's going to have a positive value. And when you do changes in molarity or changes in time, always do final minus initial. Final minus initial. Final minus initial. Final time minus initial time. Anytime that you're doing those types of calculation. Notice once again here, these are also the average rate. The average rate. The average rate. In a little while, we're not going to talk about average rate anymore. We're going to take a look at the instantaneous rate, or the rate at a particular instant. But for right now, we're going to focus on average rate for one more question. This diagram right here is available in your textbook if you have the 10th edition on page 579. You can take a look at it. It's a lot clearer in there. And you can see during this graph that this is the disappearance of C4H9Cl starting at 0.1 molar, and then over the course of time it decreases. And you can see at 900 seconds you're down to a little below 0.02 molar. And then you can see that as the time changes, rate does not necessarily go in a linear fashion, or does not decline in a linear fashion. The concentration does not decline, I should say, in a linear fashion. And we can take a graph like this of concentration versus time and get used to looking at a lot of graphs in this chapter, because that's most of the way we look at concentrations and times and the changes in concentrations and times. And we can calculate a couple of things from this. First of all, we could take a look at an average disappearance of C4H9Cl from perhaps 0 to 500 seconds. We could look at the initial 0.1, and the final at here would be about a little below 0.04, and we could do the same thing we did in our last couple of sample problems, where we said there's 0.04 minus 0.1, and then divide that by our change in time, which is 500 seconds minus 0, and we would have our average rate of disappearance. Okay, our average rate of disappearance of this reactant right here. But let's take a look at sample exercise 14.2. It says, using this figure, calculate the instantaneous, notice the word, instantaneous rate of disappearance at time equals 0. This is also given a fancy name. It's called the initial rate of disappearance. And notice what they've drawn. You can see it in color here a little bit. Your copy's not in color, but if you look in your textbook on page 579, it's in color. You can see that they've actually drawn a line in here. I'm going to kind of highlight it here in blue. And this line is drawn so that it's exactly tangent to the curve right here at 0.1 seconds. And then they drew a triangle like this. And then knowing the rise and the run right here, you could find the slope of this line right here, which is equal to the instantaneous rate at that particular point. At that particular point. And if you use these numbers, that are given on the triangle right here, and we look at the initial and the final concentrations, the final concentration is 0.06 molar. The initial concentration was 0.1. This is molarity again, divided by our time that's taken place, or time that's changed. You'll notice here at the bottom of the triangle we're at 200 seconds. That's the final, minus the initial, which was of course 0 seconds. And now we have the slope of this line right here that's exactly tangent to this curve right here at the point of 0.1 molarity. So 0.06 minus 0.1 divided by 200 turns out to be 2 times 10 to the negative 4th molarity per second. And this is known as the instantaneous rate at a particular point on this curve. This instantaneous rate is the thing that we're going to focus on almost always throughout this chapter from now on. There might be an average rate question now and again, but anytime we use the word rate now, we're going to talk about what is the rate at an instant for that particular substance. And most of the time we focus on the initial rate as well, because that's when we know the concentrations of things right at the start of the reaction. And as this curve suggests, as general as the concentration decreases, it doesn't decrease linearly the whole time. It decreases kind of at a curve rate as well. Here's the second one. Use figure 14.4 to determine the instant rate of disappearance at t equals 600. Notice here we have a line drawn tangent to the curve right here at 600 seconds. Right here at 600 seconds, you can see this triangle drawn right here. And so what we need to do is we need to find the slope of this line that's exactly tangent to the curve at that point. And so we'd find our I guess you can say, lengths of the triangle right here to find the slope that changes in y, and divide it by the change in x to find the slope right there. And if you do this, I'm not going to do the whole work, then you'd end up, well, I guess I will do the whole work. We start at 0.02 minus 0.04 for concentrations. Divide that by our change in time, which is 800 to 400. And we end up with a molarity per second, and 0.02 minus we end up with about 5 times 10 to the negative 5th molarity per second. You can see that as the reaction proceeds, the concentration per unit time, or the rate, actually decreases as well. The rate here, of course, is smaller or slower than the rate was here, which is to be expected because what's happening to the rate of the concentration of the reactant? Well, the concentration, of course, has gone down, and as you have a lower concentration, the reaction rate is slower as well. The figure above shows two triangles that are used to determine the slope of the curve at two different times. How do you determine how large a triangle to draw when determining the slope of a curve at a particular point? Well, this is a really good question, because really what we want to know is we want to know the ratio of rise to run of this particular line that's tangent to a point. Or tangent to the initial concentration. And truth be told, it doesn't really matter. It's your choice. It's your choice. Just draw it large enough, your choice. Just draw it large enough so that you can see. I mean, if you draw it this big, that's fine too, but just draw it large enough so then you can see what the x-axis change would be and what the y-axis change would be, and then the ratio is going to be the same as if you drew it this size as well. By ratio I mean the division of rise divided by run, or y divided by x, y divided by x. You'll still end up with, as we did right here, with 5 times 10 to the negative 5th, whether you draw it as this small triangle right here or whether you draw it as this large triangle right here. It's arbitrary, your choice. Look at the reaction below. How is the rate at which ozone disappears related to the rate at which oxygen appears in the reaction? Remember how we said we were kind of going away from stoichiometry in this chapter? Well, I kind of lied to you a little bit at the beginning, because we still use stoichiometry to take a look at the rates of appearance or disappearance of reactants or products. In this case, we can see that there are 2 ozones for every 3 O2s that appear. And so we could say for every 2 O3s that we lose, there are 3 O2s that appear. And if you want to write this as a fancy mathematical statement, you could write it like this and say that the change in the concentration of O3 versus the change in time for every 2 of these that are lost, I put a negative sign there saying that they're lost, we will gain 3 concentrations of O2 per change in time. Notice I used a positive sign to say that those are gained. So the stoichiometry right here can tell us how much is lost versus how much is gained. So in letter B it says, if the rate at which O2 appears is 6 times 10 to the negative 5th molarity per second at a particular instant, at what rate is O3 disappearing at this same time? So we have 6.0 times 10 to the negative 5th molarity per second. For the disappearance, I'm just going to write O2, okay? And O2 is, I'm sorry, for the appearance of O2, so I'll put a positive sign there. And I could multiply this by a ratio of the stoichiometry right here to find out how quickly O3 is disappearing. So I can make a ratio like this and put O2 in a position where it's going to cancel. O3 is my new set of units. And for every 2 O3s, there are 3 O2s that disappear. So 6 times 2 is 12, divided by 3 is 4. So 4 times 10 to the negative 5th molarity per second. And I technically should put a negative sign here because this is the disappearance of O3 as compared to the appearance of O2. So notice how I can use the stoichiometry of the reaction to let me know how fast something is disappearing versus how fast something